Hey, this is Chen, and this is my Lab 9 on 2D spring motion. So our problem was to model the 2D motion of a spring in the new video, and then compare the model predictions with analyzed data by plotting the tracker data on the same graph as the model. So our main result was that by using the momentum principle and what we know about springs, we can successfully do this, and if we use the energy principle, we can also calculate the potential energy of a spring along with the gravitational potential energy and the kinetic energy of the mass. Okay, here are the relevant models. First off, the momentum principle, which we use to calculate the change of position, and F net is calculated through the force of the spring plus the force of gravity. Then we have the energy principle, delta E equals work, and below that we have the formulas to calculate spring potential energy, gravitational potential energy, and kinetic energy. Alright, here's the tracker video, and the only initial setup things we really have to worry about are that the origin is set at where the spring is fixed, the frame rate is 10.5 seconds, and the point mass is set at the center of the mass. Okay, here's my Python program, and we're just going to run through it real quick. Here's where we create both of the balls and the other graphic stuff. And this is where we start getting into the initial conditions. Here's the initial position of the ball. Here's where the program loads the spreadsheet data for the second ball. These are the constants we calculated in the last lab for the spring. These are the initial values for all the energy values. And this is where we go into our loop, and delta T is set at our frame rate divided by 20, and it goes for as long as the video lasts. We calculate the force of gravity and the force of spring to get F net, and from that we update the position of the ball. This is where we update the values of all the energy stuff, and this is where we plot all the values that we get. Okay, so I'm going to go ahead and run my program now. And we can already see that the model and the actual data are almost a perfect match. And if I pull up the legend, the bottom two lines are the Y positions and the top two lines are the X positions, and it's color coded so you can see which one is which. And it's almost done. You can see that they're still pretty much almost right on top of each other. Okay, so now I'm going to look over the what does it mean questions. And so for the first one, it's looking at the periods of oscillation in both the Y and the X direction. So for the actual data, the value differs by about 0.1 seconds, and then for the model just a little bit more. And this is due to the fact that the spring loses less energy in the X direction due to the force of air resistance than it does in the Y direction due to the force of gravity. Okay, so the second question asks us to calculate the work done by the surroundings, and now our system consists of the spring, the mass, and the earth. So by looking at the energy principle, we have delta E equals W, and if we neglect air resistance, then the change in energy is equal to 0. From that, we have that the change in kinetic energy plus the change in potential energy is equal to 0. And because the kinetic energy doesn't change, now we're only focusing on the spring potential energy and the gravitational potential energy. And if we look at the graph from Python, it's basically a graphical representation of what I just said. The spring potential energy and the gravitational potential energy are basically mirror images of each other, so they end up canceling out. And if we look at the blue line, which is the kinetic energy, it has the same value at the beginning and end, which means that it didn't change. Okay, so finally we're going to look at what happens if we change where we set the origin. So originally we have it set here, but now we're looking at if we set it at where the center of mass is. And so if we do this in Python and run it, essentially nothing really changes in terms of all the physics. And here's the graph of the energy values, and once it finishes running, it basically looks the exact same. So yeah, that pretty much wraps up the video. Thanks for watching.